No. I have like a folder.
All right, we continue with our tutorials. So that's the second tutorial from the board today. All right, guys. So second round. Let's see how it goes today. Yesterday, people asked me to sort of maybe put the example of how to basically tune a simple neural net to this function with this data. I put the link here. If you click on this, it should take you to some gibberish thing in Google, but then up there it says something like opening Google Colab, and you should be able to see sort of the notebook where I have implemented this so that you can revise that. So before I start, maybe are there any questions? I don't know if you had any chance to kind of play a little bit further. Do you have like any outstanding question that you want to clarify, even if simple things are, yeah.
I don't know if that's something we're gonna.
Yeah, go ahead.
But like for an example, we trained the data and we were able to reproduce roughly sine of 4x. But of course, as far as I know, a part of machine learning or neural nets is to try and do some kind of generative prediction. So I didn't try it, but how good would it be if we tried to expand it instead of from 0 to pi, we gave it a new data. We tried giving it x beyond pi to 2 pi. Would it be able to keep oscillating or probably not?
So the question is, if I have shown to the network, if I want to predict the values, if I feed to the neural net values of x that is above this, then my expectation is that it will be gibberish. It will be something crazy because that's an unknown region. So that will be extrapolation region. I think that, for instance, another complementary similar exercise is if you have carved out in the middle and don't show a range in x, then I think that the model will probably perform well simply because it will be an interpolation. So interpolations are better than extrapolations. That is true even if we are not doing a neural net. It could be any parametric model outside of extrapolation will be extrapolation. Right. Yeah.
And so you have more data in that region. How much data would you need to train the model? Would you need still 100 points in that region? Would you need 10 based on its knowledge of what's going on from 0 to pi?
I would still think that it would be gibberish in the extrapolation region. So you will have essentially infinite amount of data. I don't think that the model is learning the sine function per se. It is just basically trying to mimic locally the region where the data is presented. So I think that those two questions are important because uncertainties in extrapolation cannot be taken seriously, in my opinion. So if you want to maybe predict slightly above pi, epsilon away, probably you would still be in a reasonable range. But if you go 10 times, it won't be like much nonsense. Yeah, Peter.
So basically, my question is the same. But why doesn't this happen? Because in general, the construct is so flexible that even between the two sampling points of the sine function, you could have ginormous oscillations, right? And your model would be able to describe it, right?
Yeah.
But why doesn't this happen?
That's a good question. I don't know. Maybe you can try to decrease this 100 to a 10 so that you only show 10 points, right? And then probably my expectation is that if you try to predict in between the points, you will see that phenomenon. But at the point where you have data that you're training, it will match. And again, ultimately, whether that's good or bad, that's problem dependent. Is it bad for your need? If the answer is yes, then do something else. Right? Okay. Alexa has something that goes predictions above and is completely nonsense, which is consistent with what I just said.
That's my model. Maybe your model is better.
Any other question? Do you have a question? Okay. Any more questions? Yes.
If you are reproduce like fitting a lot of data with a model, but it starts to doing like that kind of behavior, touching each point, how do you know if you are overfitting?
Right. So in the setup that I gave, I'm pretty sure I'm completely overfitting, right? Because I want to minimize exactly that. So the technique that people use is to partition this sample, this training sample, into a training and validation. And I think I said that thing yesterday, that the loss curve for the training data will monotonically decrease, approximately decrease. And the loss function for the training set will eventually go up because you are hyper optimizing the neural net to your training data at the expense of start eating the statistical noise. So you can try to use techniques such as this one, like to prevent overfitting. There are other tricks that I know on the market that are like dropouts, which is an additional thing that you put in between the layers to set some of the weights randomly to be 0. And that has been shown to also prevent overfitting. But those goes to the art of how do you build a neural net. But again, yesterday's lecture was more about getting kind of warm-up exercise to make sure that you guys know how to use Torch. And that today we're going to maybe spice it up a little bit, hopefully. Any more questions before we get started? No more questions. So, right, let's dive in. Okay, so I changed a little bit the titles. So we are going to be doing generative AI, and we are going to try to work with normalizing flows. I will try to work with you in the next hour or so, or plus 10 minutes, how to do the implementation. And maybe tomorrow, we will work more on the example usages, okay? So there will be, again, as yesterday, there will be places where we will stop and we will kind of play with the code. But I think today I have to give you a little bit more slice from the perspectives or the theory behind this. So how many of you have ever done something like this? Raise your hand. All of you. No, almost all of you. Great. So for those who hasn't done it, it's a great opportunity to do this. So the first line here does essentially generates for you a bunch of values of x that are distributed according to the normal density with mean 0 and standard deviation 1. That's what this line does. And you can put even 1,000,000 here, and it will generate that x instantaneously, right? It's a great tool there. However, what if you want to actually generate samples that are distributed according to a different mean and different standard deviation? And the standard trick is to put this pi plus 2x. Is this clear to everyone? That trick, why that trick works? Okay. And essentially, the x distribution, if you actually do the histogram, it will look like this. And if you actually make the histogram on the y, you can see that the mean has been shifted to 5, and the width has increased by a factor of whatever I put there. Sorry, this is 5. Maybe I have changed from slide to slide. Okay. This thing here in data science has a name. It's called reparameterization trick. Everyone has used it, but no one know, typically you don't know the name of it. It's called reparameterization trick. What's so good about that stuff? The first thing is that mathematically the base density is this guy here, right? Because it's mean 0 and standard deviation 1. You also know exactly what is the probability density for this guy, right? So for problems, for certain problems that I'm going to discuss in a bit, knowing the probability density on a space where you want to go is important. And you want to also know how to sample it efficiently. So if your target density where you want to go is also a Gaussian, then this is your answer and you can stop doing anything else. That's the end. But what if the density where you want to go is more complicated than a Gaussian? And that is the subject of today's implementation. Okay. So this is where you need to use something called normalizing flows that I will try to walk you through. Now you might say, why should I care about that? So the primary reason you want to use this is in the context of Bayesian inference. And unlike many other fields that embraces this paradigm of Bayesian inference, our field still not uses that thoroughly, which is very strange. And that's why I thought it's important that in opportunities like this, people start using techniques that allow us to use Bayesian inference.
But based on my very, very limited knowledge and background on the Bayesian stuff, is picking up it's the prior that you pick can really affect the posterior that you get. And then sometimes between collaborations, people don't quite necessarily make sure that they use the same things. Unclear to me, but like I'm talking at least in neutrino. Neutrino is all beta decay. That was my understanding. And then when it came down to like taking physics messages away from that, I never knew, I guess in like when we do these Bayesian inferences, I don't know, like how can you make sure that everyone is on, I guess, in the same page? Is it possible, or LHC, or how has it been in your experience, at least so far?
So I think the short answer is no. You can't make everyone to be on the same page. I will argue that there is no such thing as a ground truth that you can actually get. Is all, data science tools is just a tools that allows you to sort of define some confidence levels that are reasonable. And Bayesian inference is sort of the underlying machinery that operates to reconstruct the quantities that it was discussed in this summer school, such as PDFs, TMDs, and GPDs. You are inferring that primarily because it's an inverse problem. You can't actually solve in a closed form the PDF, the TMDs, the GPDs using experimental input data. That's not really possible. The only thing that you can do is to infer them. And when you try to infer them, then necessarily you have to go to the pipeline of a Bayesian logic. That's sort of the reason why I'm bringing up this in this context. Now, there are other contexts such as single parameters when you want to get the mass of the W, something like that. You can still apply Bayesian logic, but you can also approach this thing from the frequencies perspective too, which is essentially saying the prior is 1. So you can agree with the frequencies by saying we don't care about the prior. The technical aspect that I'm interested for the normalizing flows is for sampling the posterior, regardless of the prior. Prior can be 1, but I'm interested in sampling, and I will explain this thing in a bit. There are other applications. If you are interested, for instance, in constructing like a fast Monte Carlo simulators for phase space generation, you can also do this stuff because you can actually use the normalizing flow to generate inclusive events. You cannot generate technically exclusive events. It's possible if you use something called deep sets, you can actually make sure that you can generate different sizes of particles per event, and why not? So this is another application. And then another application that this is where I actually learned about normalizing flows was from lattice gauge theory, because essentially lattice QCD is a sampling problem. Okay, and so normalizing flows has been one of the techniques that lattice people have identified as a way to sample an enormous amount of degrees of freedom in lattice QCD. Okay, these are the motivations. Do you have any questions in terms of the logic so far? All good, more or less? Ask me any questions, because I want you to sort of, I didn't spend too much time about justifying why do we need, the normalizing flows, because I want to spend more time on the implementation level. But it's always good to have the question about why you're doing that, right? So actually, I did have one slide that tells you a little bit. So the quantities of interest, because there are so many things like parton densities, GPDs, TMDs, fragmentation functions, et cetera, let me just summarize those names as quantum correlation functions, so QCFs, okay? Namely, these guys. And we always have to do some modeling for them because of the inverse problem. And the modeling of the QCFs contains some parameters, theta. And the goal, what observational data does to us is that it allows us to define a probability measure in the space of theta. That's all about it. There is a way to construct a probability measure, which is a manifold in the space of theta, where theta can be arbitrarily large in dimension. And all we are looking at in terms of Bayesian logic is to be able to construct that, analytically, this probability measure. And that's what the Bayesian logic will give you. And so Iris was talking about the prior. You can set the prior to 1, or you can say, I don't want to pretend that I don't know absolutely nothing, so I'm going to put some prior because, for instance, the theta parameter has to be positive. So if it's negative, it doesn't make any sense. So you can put a prior there to restrict this posterior density. This likelihood function, I don't know if I have an equation there. I do have. Typically, you can define a chi-square, like something like a data minus theory square, right? And that gives you the likelihood function. And that's it. You have now a probability measure in the space of the parameters. And let's say this is like maybe 20, or it could be 200 dimensional. In parton densities, it's easy to get all the way to 200 dimensions, for instance. So what you want to do, okay, you have this probability measure, and what do you do with it? Okay, because it's analytically defined. Well, the first thing that you have to do is that you have to sample the parameters from this probability measure, because you need to play with this. And in order to do that, you need to sample the parameters. That's the only way technically to do it. And so this symbol here tells you that you are sampling theta parameters from the posterior density. You are going to plug these theta parameters into your QCF model. So this could be PDF, GPDs, whatever physics you want that has some parameters. And then you can imagine that, for each theta, there is a realization, and then there is a transformation from this theta space to the QCS space that look like that. And in this space, now you can say, okay, I'm going to define a credible interval. So Bayesian statisticians typically define something called the Bayesian credible interval, which is a fancy name just to say, let's compute the CDF of this distribution. And you can say, here is my 98 confidence level for this object given the data. That's essentially the rudimentary things that we do in Hadron structure that I do this thing for a living. Okay, I get paid by doing this. Now, so the question is, how do you sample these parameters? I have this guy. I can write it analytically. By the way, this is a proportionality, is because in principle it's not, it has to be normalized. I don't know the normalization, and that's perfectly fine. How do you sample that? This is not a Gaussian, just like the example that I showed before. This is a more complicated stuff. So the task is that I want to construct a normalizing flow that mimics this distribution so that I can sample from it. That's the idea. Okay, so this recipe is going to be useful for any of you who ever try to connect data and theory, because you are always bounded to this task, to infer something from data. There is no other mechanism that we know about it. This is the only thing that we know. So the problem is that normally what people does is something called fits. I'm going to fit my model. And technically, fitting a model to parameters means doing a maximum likelihood. What it means is to go and find the theta that maximizes this guy. Finding the theta that maximizes this guy is equivalent to maximizes, let's say, this guy. And notice that this guy is in an exponential. If this is big, that means that this guy has to be small. So the maximum is the minimum of the chi-square. And then you take that theta, and then you tell your supervisor, whoever that is, here is my result. And that person will tell you, what is your uncertainty? Oh, I don't know. I just did a chi-square minimization, and I get that. I didn't know anything about errors. Well, there are a lot of things that probably Fred talked about in terms of how to, construct confidence levels using Hessian method and why not. The standard everywhere outside of nuclear physics, particle physics, is to go to sample this posterior. And this is something that we don't do much. I think that I'm being cynical. For instance, in heavy ion physics, there are people who does a lot of Bayesian inference, and they will recursively use the sampling algorithm to do that. There are algorithms that you can do it. It goes under the name of Markov chain Monte Carlo. It is extremely painful to actually make it work, okay, typically. It's not, okay, in lattice queues, it is even more painful. But in sampling problems, it's extremely painful primarily because the evaluation of the chi-square can be extremely cost. So you take a lot of time to basically evaluate this function, and it's generally a difficult problem. This is where the normalizing flow comes in and helps. And that's why I'm giving you, hopefully in the next 30 minutes, a snapshot of how to build a normalizing flow and so that you understand the mechanics. And it's actually quite fun, as I hope I will try to demonstrate. Okay, so the main idea came from this paper. You can click on this. This guy is from Google. Benjo from Google is a genius in ML, and he came up with that idea, okay? And later, our friends in lattice QCD has adopted mechanism around this paper. So what's the idea behind normalizing flow? So first we start from a continuity equation. Essentially, it's a change of variables. Okay, so we go from X to Y, and you have to implement a continuity equation because you want to guarantee conservation of probability. So this is a probability mass. If you change the variables, it has to conserve the same probability mass. And all you have to do is to move this guy to the other side, right? And then I'm going to just flip it, put a -1 here. And there you go. What you call it, this guy is called the base density, and this is your target density. Okay, so far, I hope people are not lost. This is just ordinary calculus, nothing complicated. What's so interesting about it is that imagine that the base density is a Gaussian that you can sample very easily, just as like NumPy random 1000. So you can generate a bunch of X values, and all you need is a recipe to transform that X values that you generated into Y in an efficient way, okay? And then if you can do that, then, and if you can compute the Jacobian, then you have access to the target density, literally the probability, as well as the samples. So just to make sure I explained this well, you see, I said here that I can generate a bunch of X and transform into Y space very efficiently. And here I know what are the probabilities. So if my problem were a Gaussian center error of 5 with standard deviation of 5, I don't have to do anything else. But if it's not, if it's something more complicated like like this kind of likelihood, then you might want to use a normalizing flow. So the rest of the talk is about how do I construct this mapping from X to Y, and how do I construct this Jacobian. Okay, and this is where the paper tells you about this affine transformation. Okay, so what's the idea here? You have here, let's say, a bunch of features X that let me write here. So X goes from, there's this notation 1.d, which is nothing by saying this is X up to XD. That's basically the notation. Okay. And there is somewhere in between here a little case XD lowercase. Okay. So what this notation tells you is that I'm going to essentially transform only the features above D. And the other features I'm going to get fixed. Okay. The pieces that I'm going to transform in this particular way. So notice the structure. I'm going to multiply the let me see if I have, yes. So this is a better an example. Suppose that X is basically a 5-dimensional vector, okay? I'm going to pretend that 1 to D is these 3 guys. So these 3 guys goes into these 3 guys. These 2 guys are these guys. I'm going to transform it via this. Now, this notation is a array-wise product. So that means that this S of X1D, S is a function that receives these guys, and it will map into a space of these 2. And I'm going to do array-wise product, okay? And then I'm going to add something. So because I am multiplying each entry of these guys by a factor, this is just a rescaling. And I am adding another number, so this is a shift. So I'm just doing a rescaling and a shift in this affine transformation. So this S and T, turns out, are just essentially neural nets. So for this guy, you will take the X1, 2, 3 from this guy, right? And it will map into, this is not exactly true. So this, okay, ignore these labels here. 3 has to go to 2 because this thing here has to be a vector of size 2. And I have to have 2 exponentials that I multiply this guy to get to here. Okay? And then this T will do the same thing, and it has to go into 2. So it's a neural net that goes from 3 to 2. And I explained yesterday that you can build any neural net, deep neural net, that goes from whatever you want. In this case, it will be 3 to 2. And in between, you can put whatever you want. Infinite layers, infinite neurons, etc., etc. Any questions on this part here? Yeah.
So in the second line, okay, so X1, X2, X3, those don't get rescaled and shipped. They just get somehow translated to Y1.
Just copy.
Copied, okay. So then YD plus 1 to D, so that means, or yeah, Y4 and Y5 look like they take X4 and X5 and do some rescaling and shifting. So why are S and T from X1 to D rather than XD plus 1 to D?
Good question. I'll tell you in a minute why. But for the time being, this is the transformation.
Okay.
All right. So, as usual, there is a collab exercise. So let's code it up, this affine transformation in collab. Okay? You guys know how to build a neural net. So I gave you the examples. You don't have to stretch your imagination how to write this. You can just copy and paste whatever I wrote here and just play around, maybe take a minute to see that you can actually show that you can write in the Torch language what I just said there. So let me explain a little bit the magic here. So I'm going to use the example before, we have 5 features and we are going to freeze 3, right? So lowercase is 3. The S has to go from, the S has to go from 3 to 2. So let's see, it will go from 3 to 5 minus 3, which is 2. Okay, so this is just an S. And what do you do with these guys, tanh or R? I leave it to you. And then for the T function, I do exactly the same. It's a different function. Receives 3 and 5 minus 3, 2. Right? Now let's look at this forward. The forward function will take the X, which is the column of X1, X2, X3, X3, 5, and it will try to map into this guy that is written here. So let's take a look exactly what I did here. This line here is called a mask. Okay, I will try. Hopefully, you understand what I'm talking about. This 1, 1, 1 here is for me to indicate that the first 3 entries of this X are going to be kept equal, and the other 2 are going to modify. So the first thing I will do is I will create an empty array full of zeros of the same side of X. Okay. Then I'm going to copy the first 3 entries of X. I'm going to copy it into Y. Do you understand that this is equivalent to a copy? I am just adding to 0. That's equivalent to a copy. And I just want to make this copy in locations where this B is equal to 1. Only this. Okay, so the first 3 entries of the X get copied into Y in this line here. Next, I want to construct this S function. So I need to feed, again, this X, 1, 2, 3, only in locations where B is 1, 1, 1. So I feed this guy, and I get the S. This has to have a dimension 2. You should check it out. Just print S, and it should give you 2. An array of 2. Same thing for T. And once I got this, I'm going to try to modify the places where I have zeros. So in the Y array where B is equal to 0, first take the X values where B equal to 0, which is these last 2 entries, multiply by the exponential of S and add T. Okay. Any questions there? Or too complicated? You guys follow? Or totally lost? All good? Don't be shy. All right. Notice that the inverse transform is also trivial. You just move the T to the other side, and you move this exponential as an inverse. So the inverse is very easy to code it up. Here is it. So it's kind of very similar to this guy. Instead of starting from X, I'm starting from Y, and I'm returning X because I want to do the inverse. The only thing that I have to change is essentially this line here, where I say X is equal to Y minus T torch inverse minus S. Okay, now take a minute, paste this code in your collab. Oh, by the way, I forgot to mention one quick thing. Sorry. Yesterday I gave you, this is terrible, okay. Yesterday I told you that these are the headers. Remove this stuff because it's going to mess up things, and add this line here, which is something that I found that it only works. So you need to make sure that all the data types is 64-bit somehow. Reasons unknown yet, but if not, it doesn't work. Just make sure that you use these headers that I showed yesterday. And I think with that, you should be able to quickly code up the one flow, one thing here. So go ahead, I will give you a minute.
Can you show us the unification to the others?
Say again?
The unification to the others. Oh, it's on the Presentation.
Yeah.
I have it open. Yeah. It changes.
Like yesterday's presentation.
Thank you.
It's the same. I haven't,
Just
I'm just modifying the same thing, so.
and where it says Latin. True. To install Latin.
Even if it is commented over, we need to.
So if you do this thing correctly, you can run these lines. And you should be able to get this output. Okay. Who has finished? Only few, okay. One more minute. Who is not trying? Okay, no, but everyone is trying, but not finished, okay.
It's because that's a screenshot.
I'm so sorry, yeah.
You have to work a little.
I know. I was spoiled by the thingies before.
Exact same.
You should not get exactly the same output. Why do you think you should not get the same output?
There's an answer.
Maybe because the seed change for every PC, so the starting point is different for every.
The seed for what?
For the X function.
For this function,
Yes.
right? This is a neural net. Inside this, there is a weight matrix, a bias, and those are initialized randomly. And so essentially, if I run this in my laptop and you run it, those are architecture-wise the same, but the matrices inside is different. And if these guys are different, then when you do this operation, even though you're using the same X, you might not land on the same spot. That's the reason. But it's important to ask those questions. You have to understand why things change or not. Does it make sense? In this case, it makes sense that you get a different answer. Everyone good with this? Raise your hand who couldn't get to this point. Few people could not get to this point.
No,
okay, done.
I'll help. Done.
I know we're gonna get there in a second, I guess. In the yesterday, we were just making a neural net to do something, and the results kind of seemed like they could be anything. And we gave it some training data, and we realized that a neural net can help us fit to data.
Yeah.
And that was the point, I guess, of whatever it was called yesterday.
Yeah.
Normalizing flow, we're just trying to change target parameters.
We will provide a target density, and we want to try to mimic that. So right now, I'm just building the normalizing flow architecture. So no data yet. Once we get there, we need to optimize these neural nets to make it work. Right? That will be the idea. All right. In the interest of time, couple of things to note. I'm printing Y, and I am printing backward Y. No, sorry. Yes, I'm printing backward Y, and X is 0.1, 0.2, 0.3, 0.3, 0.5. So as we said, the first three entries are going to be copied, right? That means that I should be able to compare the first three entries with these first three entries, and they should be the same. That happens. But I'm going to modify the last two entries, and therefore this 0.4 and 0.5 now becomes 0.5009 in my laptop and 0.63, 0.06. So it is behaving as expected. I'm only changing the last two, right? And moreover, I am trying to see if my inverse transform is operational, if I take this y and feed into the backward, I should obtain x back. And notice that this output, 0.1, 0.2, 0.3, 0.4, 0.5 is identical to this. Yes.
So this would be kind of like, say, if I give it a, what is this thing? I forget what it's called. It's gonna be in my head, but basically like when you reconstruct the jets, unfolding, where the physics itself is, while you're reconstructed has all of the detector effects and all that smearing. So you end up with this like big matrix that, given that specific PT and that specific rate data and whatever, go back to like what the actual physics was versus the what you reconstructed, kind of like that, how in,
It's like
yeah, a little bit, I don't know.
unfolding is way more complicated than this. This is
Oh, okay.
just a linear transform,
Fair.
right?
Like, okay,
I will make this thing more, more interesting as we go along, but this is the pieces that you need to understand
fair.
first.
Get S and get T are both neural nets. We made them right here. And that means every time we run them, they have new weights, randomized weights.
Every time that you initialize them,
Okay,
Right.
because my question was gonna be, why does backward give it the exact opposite if the weights are different every time, but they get initialized once?
the backward has to always give the same thing as the input. This input hasn't changed.
Right, but it's written just use the same neural nets. I guess I was under the impression that the weights changed. The weights were randomized every time you run the neural.
Oh, no. So when you press shift and enter on this, you're instantiating a neural net and all the weights and biases are now frozen. Right? If you shift enter again, then you will be instantiated again, but with different weights and biases. But this is, once you instantiate, you can, when you evaluate the model like here, it's deterministic. It won't change. So if you run this thing twice, you have to get the same number because the weights and biases are frozen. So instantiation, evaluation. In evaluation, weights doesn't change. In instantiation, weights and biases changes. Okay. I feel like I'm very bad in time, but let's see how it goes. So, okay. So imagine that, so we are doing this, and let's say that this is the only transformation, the transformation that I'm doing is just this, okay? And what's so cool about that, and I will get back to Nick's point, why I need to write that transformation as it is. The base density could be a Gaussian, so that's nice because I know the actual PDF for the Gaussian, and I can sample the Gaussian very easily, namely this. I will argue that we can compute this Jacobian very easily. And that's the answer to your question, but I will explain a bit how it works. And also the transformation is invertible, as I just demonstrated. So let's try to digress a little bit about the Jacobian, why the Jacobian is easy to compute. So this is my imagination of the Jacobian. Recall the Jacobian, dy1 divided by dx1, dy1, dx2, and so on and so forth. Right? So and now we need to fill this matrix. So let's try to imagine what is the first entry here. This is dy, and just to make, couldn't write it. So dy1, dx1. That's the first entry there. What is that number according to this transformation? Wow. Great. What is the next entry here?
0, 0.
Very good. What about this guy here?
1. 0, 0.
All right. What about this guy here?
1.
Very good. You know how to do calculus. What about this guy?
have to think about it.
Okay. What is the derivative of dy4 with respect to x4?
0.
So derivative
Oh, wait.
y4
It's exponential.
x4.
Yes.
So this guy will go 1. This is 0, and it's just this exponential. Right?
So random, every time you initialize your neural net, it has to be different.
Yeah, but for the time being,
Oh, yeah.
the big point is, what's the derivative? It's just this exponential. And what is this guy? But it will be the same exponential?
No.
Because this guy is an array of 2, right? So it would be the first entry of this array will be here in an exponential form, and this is the other one. So good job, guys. You know calculus. It should look like this. Okay, that's definition of an affine transformation. That the Jacobian transformation is what? Lower triangular. Because these are not zeros. Sorry, these guys here are not zeros. But it's lower triangular. And what is the determinant of a lower triangular matrix?
Of the element, the diagonal element.
Yes. So you don't need to know anything about it. All you need to know is the diagonal. That's it. So, okay. So there is a miracle. So the Jacobian is essentially the product of these two exponentials. Exponential is positive, so I don't care about the absolute value. I can combine the exponentials, so it becomes exponential of the sum of the s's, right? Therefore, the Jacobian is very trivial. It's the exponential of the sum of this array. If you, as Nick suggested, but why you put here x13 and maybe not x45, then you are not going to get the affine transformation. The Jacobian will be not lower triangular. That's why you have to put this guy here from here. That's the idea. Okay? Let's see what else I put here. Oh, coding exercise. All right. So what I want you to do is to code up very quickly the Jacobian. So all you have to do, and apologies, I didn't have time. I was too entertained by a base talk, so I couldn't color it. It's the same forward function that you coded up. All you have to do is to compute the logarithm of the Jacobian, which is just the sum of the s's. So you already have the s, just sum them over, and that should give you the Jacobian. So give you 5 seconds. So you can do the same thing for the inverse transform. Now for the inverse transform, it's not going to be the sum of s, it will be the sum of minuses because the Jacobian moves the exponential into the other side. Is that clear to you guys? Yes? No? Let's see. So it's here. So imagine that we do the inverse transform, right? So you move this guy to the other side, and then this guy will appear in the other side as an exponential of minus s. So the transformation is still affine. But then the diagonal entries, instead of having s, it will be minus s and minus s. And that's why down here, you have to put sum over minus s's. Is that obvious? Okay. All good? I hope so. I'm doing very bad in time. Okay. So, okay. Yesterday, one thing that I noticed was not all of you, but some people have difficulties in understanding batches, the inputs to the model. So if you actually feed this tensor, we just show that it works. It will return this Y, which is a transform, array, right? Because I'm working on a 5-dimensional problem. So what I want you to see is that if I now change this problem to this problem, it is still 5-dimensional, but I'm feeding 3 examples. So I have 3 rows with 5 columns. Feed this thing into the model, and the model will crash. Check it out. This is a coding experience. Check it out. It has to crash. Does it crash? I hope it crash. Yes? Raise a hand who got a crashing behavior when you feed more than one example at a time. You? All right, people are, yeah, it's crashing. The crashing exercise. Okay, let's try to understand why it crashes.
What if it doesn't crash?
If it doesn't crash, it means that it's not this. It has to crash. This example won't crash. This example will crash.
Oh, yeah, okay, no. Okay, yeah, that crashes, yeah.
Right? What it means is that your forward functions is not accepting a batch. You cannot feed more than one. So the next exercise is, let's try to fix it. So the way to fix it is very simple. Just go and add this dot, 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 dot. And here, put a view minus 1, 1.
You have to do it on the backward too, or just forward?
Both. I want you guys to be able to build the forward and the backward to be accepting batches. Any questions? Why? Say it again.
The view method. What is doing?
Okay. So if this x is 3,5, that means 3 examples of 5 features. I want to go into this y, which is the transform sample. I need to have 3 examples, 5 features, right? Now, the Jacobian, oh, by the way, you have to also add this dimension 1. Because in the previous case, I show it without this dimension, right? What I want is to sum not over all s's, because this s is now a matrix. And I only want to trace it across the columns. That's why I put dimension 1. And now I want it to turn into a view that is a column vector, so that I have 3 values of the log probability. So this y will be like 3 rows with 5 columns, and this Jacobian will be 1 column with 3 rows. That's the idea. And if you do that, it should look like this. You see? You have, okay, sorry, I said in words the expected behavior. The output is 3 rows, 5 columns for the y, and 1 column, 3 rows for the Jacobian.
If I put this dot dot, then I'm getting the error in the first one.
Yes.
But why?
Why that happens? Yes. What you can do is you can put a parenthesis here so that this guy becomes like a batch, but with 1 example. Okay, that would be the way to fix it. Again, I discussed this thing yesterday about the 2 modalities, batch versus single mode. This is one of those places where we have to pay attention to it.
So in that case, the B would apply to like the first element. The modification would only be to the last two examples, right?
Yeah, this will modify the
So I'm thinking like a vector of vectors.
Oh, yes. So here, the X that I have generated, these guys are the same for this X. And these guys are going to be modified.
Okay. So it's the okay.
Yeah. Okay. How much time I have? I'm allowed.
5.
Oh, 2:05. Okay. Okay. I thought I have to finish now. Okay. Okay. So this is just a recap. You have at your disposal basically 3 building blocks. You have the neural nets, the S&T for the transformation, and you have this forward and backward that allows you to implement the transformation. You can easily change your dimensionality by putting 10. And then that means that you have an X array that has 10 entries, and then you can decide which one are frozen and which are not. Any questions at this point on a technical side? I know that you might be, so what? What is the whole point of this? But technical points. No question. So if I were you, I will be asking, so what? For instance, you just said that you are going to transform 5 dimension into another space, but you're freezing the first 3. That means that I am not changing the first 3 degrees of freedom, only the last 2. So nothing happened to that part. And that's inconvenient. What should I do? And the natural answer to this is add another flow where you flip the roles. So what you can do is in flow 1, we keep these guys fixed and modify these 2, and apply another flow where you reverse the order so that you modify these guys and keep fixed. So the equations go from here to here. And that's how you do it. You just add more flows, and in each flow, you fix certain things, free the other ones, and so on and so forth. Is that clear, more or less? That gives you an ability for you to transform all the features, okay?
You don't want to transform all the features. Why don't you just change all of them at once?
Because then it's not an affine transformation.
It's not a what transformation?
It's not an affine transformation. Let's see. You see, that's a good question, and let's try to understand that question, okay? What he's asking is, why not we have only one equation in which we have 1 to 5? The problem is that what do I do here? I need to have something frozen. I am bounded by this. I don't have any other solution. So you have to rely on freezing certain degrees of freedom, modifying others, and in the next flow, you swap the order. That clear? More or less?
This is all under the expectation that S and T are different than S prime and T prime.
Yes,
If they were the same, then it would be an affine transformation, right? Because then
it won't be an affine, that's correct.
Okay.
You need to have a transformation. So each flow, each thing has to have a different S's and T's. That's the other thing. Okay. So how does the 2 flow setup look like? So this is my starting point. I do the first flow and I do the second flow. I have to compute the Jacobians from this flow we just said that is the exponential of this sum, right? And for this flow is the exponential of this sum. That's it. And I know also the probability in this Y space is the base times the Jacobian. And the probability to go from Y to Z, this Z, is this quantity, right? And I can take this guy, plug it here, and voila, what you have is PZ of PX times the two Jacobians. And you can actually combine the exponentials as a sum. So ultimately, the beauty of this affine transformation is that you can keep adding as many flows you want. The Jacobian is just a single sum over all these S neural nets. More or less good? Okay. So the authors of that paper suggested yet another trick. So, we just decided to fix these three and release these two. Are there other possibilities? And naturally, if you drink a little bit of coffee and cookies, you might start thinking, well, why not I do a checkerboard, right? Why not I take the first one, modify it, the second one, freeze it, and so on and so forth. And in the next flow, you reverse the order. And you can summarize this checkerboard scheme with this formulae that is in the paper. So let's see how that works. So this is the formulae for this particular example. So let's see why this formulae is for this case. So B is going to be, and I didn't wrote it, I'm going to put B to be 1, 0, 1. I have 5, right? So
The next slide.
oh, is it the next slide? Okay, sorry. Thank you. Something like this. Okay, it's better here. So let's see. I want to check what's going on with this formulae for this flow. So I do the multiplication with X and the B. Now let's set the B to be this guy. So I will take 0 times X1. What's that? 0, right? That means that Y1 does not receive anything from this guy. You will receive something from this guy because 1 minus 0 is 1. And then I multiply by X1, exponential of, and this guy here, the B0 will only keep track of these ones, and you feed it here. Okay, and the same thing for T. And you can imagine that for the next flow, I'm going to reverse the zeros and ones, and now I'm going to pick up this guy to set this guy here. And so this equation is a checkerboard scheme. And the only thing that you have to do is to define the B and flip it every time. And then you can have flip, 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 flip. So you might say, okay, we did this enormous exercise to go from here, and now you want to change it. Turns out the code-wise is very trivial to implement this. Let me show you how. This is the only thing that you need to actually code it up. Because the B's, in the previous case, I said B equal to 1, 1, 1, comma, 0, 0. You can literally flip it, write as a 1, 0, 1, 0, 1, 0. And the reason that I am writing these lines here is because I want to define the checkerboard scheme depending on the mode of this index. So that if I said 1, 2, 3, 4, the mode will be either 0, 1. And if it's 0, then I'm going to construct zeros and add ones every other 2. So that would be 0, 1, 0, 1, 0, 1. Or if it's the other case, then I'm going to flip it. So I can construct, depending on the integer values of this IDX, I can construct different B values. Okay. So this is a coding exercise. Try to update your code, including the backward, to do the checkerboard scheme and convince yourself that the transformation on each flow is changing only the ones where you have one and zeros. Yeah.
Why is this preferable to the scheme that we used at the beginning with the threes and twos? I mean,
That's a good
I
question.
feel that it's most systematic, but
I don't think there is a unique answer to that. In fact, one of the things that I've been thinking is that you can imagine that if you want to if you're tuning parameters were pixels of an image, you want to have sort of continuity among neighbor pixels. And in that case, I will probably be using something like that, right? So that I can have I don't induce rapid transition between the pixels. But you're right that, at least from my perspective, I don't see the advantage. Okay.
and I suppose that you can add more flows, right?
Yes.
They don't have to be two.
Well, the other thing is that you might want to have all possible combinations. And so manually writing these B's seems to, in principle, you can randomize the B value in zeros. You can just create a B array with 5 entries with random zeros and ones. You need to have at least 1, 0, and 1, 1 in the array, right? But a good question. I don't know, how does it play, but I'm just explaining what the Google guru told humans how to build this model. Okay. I was here asking for you to do the exercise. So please do the exercise and convince yourself that the checkerboard scheme is working on your end. I give you 2 minutes. And if there are pieces of this code text that you're not sure, just let me know and I can. I promise I didn't ask ChatGPT to give me the code. I coded it myself so I know every single damn line of this code. Any difficulties? By the way, here I use reshape in terms of view. That's the same thing. One of the issues we touched that there are billions of functions that does the same thing. So reshape view, and there are a couple others. Okay, who has finished? Okay, then it's a good sample. So let's check if the checkerboard scheme is really working. So the B tensor that I have here is 0, 1, 0, 1, right? And what we expect is that the ones that are copied identically are the indices that has 1. Therefore, if I compare the original X and the output Y, this guy and this guy should be the same because this is label 1. And this guy and this guy should be the same because this is labeled as 1. And the ones that are in 0 should have changed. You see it? Okay. Very good. All right. So now we need to assemble. So suppose now, you're here and you need to generate like 100 flows. So you could imagine copy and paste this thing several times, which is not efficient. So it's much more simpler to write a class to instantiate the whole flow. How many of you are familiar with classes in Python? But a class in general, even, okay. So this is a way to write a class in Python. You just say class, whatever name. So let's call it flow. This is called inheritance. So you will inherit in a bunch of modules. It's not technically necessary, but keep it like here. And you need to initialize this instance. So you have to put this super init. So these two things are kind of always be there when you are building a class or a Torch ML model. And all I did was to copy and paste the previous code inside of this init. Oh, by the way, I didn't told you about this D. Do you understand why I have this D here as a sum of the B's?
Because you need to separate which of your for our two different transformations, sometimes 3 are being changed, sometimes 2 are being changed.
And
you
that
need to make sure that 2x1 matrix and the 3x1 matrix are applied properly. So
And that
in this case is summing.
Right, and that dictates the architecture of the S and the T, right? So you need to put here the D because for the 5-dimensional case, if I have 1, 0, 1, 0, 1, sorry, no, this. If I have here, that means I am modifying I'm modifying 3 at the expense of 2. So that means that this S should receive 2-dimensional inputs, right? Well, if I have 1, 0, 1, 0, 1, now I should have 3 inputs. So it depends on the dimensionality of the problem. So that's why I need to have this little lowercase d to be there. And I just figure out that just by summing the b, because the sum b is the number of things that I need. Okay. Try to code this up in this fashion. One thing in classes is that the functions needs to be preceded here in the argument with self so that you can call it later. You can also put this self here so that you can call in the forward the self, you can call it back here. And essentially that's the essence of, converting the previous code into a class. So I give you another minute to code up this class and instantiate it like this fashion and see that you can see the outputs. Take a few minutes. And we're almost done. Trust me. It's not that boring. And raise your hand if you need help, okay? The other thing I forgot to tell is that, of course, we want to create a lot of flows. That means there will be a lot of neural nets, and we want to train that, and we want to use GPUs. Therefore, you should put that device on quantities that is going to be exposed on a GPU. I think that the places where I put device should be sufficient, I believe. Okay, any luck? All good? Raise your hand if you have finished. Okay, you guys finished. All right, this is your flow. Okay, another quick exercise. Let's instantiate many flows, like 5 flows. So that will be very simple. You have your code, and all you have to do is to write a list where you instantiate the flow, and you can actually put actually you don't need this percentage over 2. Just remove this guy and just keep it as an integer so that it goes from 0, 1, 2, 3, 4, 5. So when it's 1, 0, 1, 2, 3, 4, 5, every instances you will either pick this line or this line, and then you can generate the flows. So in this way, you can instantiate 100 flows in 1 second. Just with just this thing here. Okay. I didn't put Google Colab, therefore it's not an exercise. This is how you will instantiate it. All right. The next thing is, okay, we instantiated all these flows, all these 5 flows. Now we want to chain them. Okay. We want to be able to take the first, use the first flow, pass the output to the next flow, and so on and so forth. So for that, we need to write another class, which I'm giving you here the example so that you don't have to stretch your imagination too much. Again, it's very simple, normalizing flow, right? You feed here the flow array that you instantiated in the previous slide. So, you know, you have these flows generated here, and you feed it into here. So one thing that PyTorch have this function called module list that it will essentially capture all the parameters that are inside of this flow as part of the model parameters of this class. So recall, we want to train a bunch of neural nets that exist under each of these flows. Okay, I have only 5 flows, so I have 10 neural nets, the S's and T's, and I need to modify the weights and biases of them. And I need to be able to expose the weights and biases of the S and T neural nets under each of these flows on this model. And you can achieve that just by doing this. Okay? Module list. So you have cell flows. Okay. Then we do the forward. Let's write the forward function. So in the first line, I'm going to instantiate a Jacobian that has the shape. This will be the number of examples, comma 1, because the Jacobian ought to be just a 1-dimensional column. You know, it's a 1 number per example. So I should have, you know, number of rows, examples, comma 1. And I'm going to loop over the flows that we just instantiated. In each time, I'm going to feed the X to the forward. This function that we just wrote returns the transformation that I am incidentally writing again as X, because I don't want to, it's more cumbersome if I write Y. I feed X, return X, but this is updated. And I got this Jacobian with underscore, and I am adding to the Jacobians here and go over all the loops, and I got this X Jacobian. So this is just the forward function to be able to chain all the flows. Any questions? There is nothing sophisticated here, just doing a loop over all the flows. And this is the backward version. It's very similar. So as an exercise, just go ahead and try to code up this and show that you can kind of see this behavior. Yeah.
I was more focused on like copying over the code and stuff, so I kind of missed the like quick explanation of what a flow is. This is chaining flows, and it looks like a flow based on the example. I don't know, allows us to.
So this is the generic structure of a flow. so that we can instantiate many flows. And this is just one flow with a
Right.
specific B parameter, B array, checkable scheme.
I think I missed what the point of the flow was, like why we made a class flow.
Oh, because let's say I want to build 5 different flows. That means I need to have 5 different S's and the T's. So if I keep writing in this way, I have to copy this guy and paste it 5 times.
So rather than having to shift enter and get new weights every time, we can run a flow and get five, in this case, 5 different.
Flows with different S's and T's.
And why is that useful?
Because the flows needs to have different S and the T's.
But why? Like, why do you want different S?
Because it's not an affine transformation anymore. Because that the affine transformation is from one space to another. And the next space shouldn't know anything about the Jacobian or the other. So I need to make sure that going from one space to another, I have different S and T neural nets.
Like if you're wanting to run multiple affine structures, normalization parameters at like the same time.
Let's see. So let's go to this example here, right? So here is the 2 flow setup. It's not a checkerboard, it's just 3 and 2 flow flip, right? And so I do this flow and I have a unique set of S and T. And so I go from X to Y. Now in my second flow, I will go from Y to Z. And now I need to use I'm arguing that I need to have a different S prime and T prime. Right? And so in your code that you wrote, strictly speaking, you have to write this thing over and over for each flow. But instead of writing this thing over and over, you can just write a class. A class so that you can, so I'm confused. Yes, you can write a class so that you can instantiate many flows. You can say, I want 5 flows, 10 flows, 50 flows. For imaging, people typically use like 60 flows. So it will be kind of cumbersome to copy this thing 60 times. That doesn't make any sense. So that's why you use a class. Okay. Okay, my time is getting up soon. What did I want to say here? I wanted to say something about final touches. What's this about? Oh yeah, so for instance, to make this class to be nicer, I will try to put like the D-dimensionality. Oh, now I remember. I want to write another function inside of the normalizing flow class that you wrote, so that is called sample. So that if I said batch, let's say, I can essentially first generate a bunch of random numbers in a batch, transform them through all the flows, so that I can return the transform value. And also I want to construct the corresponding PDF, because what I computed was the Jacobians of the transformation. But at the end, I need to add the log probability of the base density. So I want, you need to have this function written to finalize your normalizing flow. Okay? You should check it out, that if you code it up, you can see something like this. Okay, so to recap, essentially a normalizing flow is these 2 functions. So I think I counted something like a bit less than 50 lines, and this is less than 50 lines. And all the buzzes about normalizing flows is just this. It's very simple or not. Yeah, you have a question?
I think there's a typo, like that cell B, I think it's indented too much.
Should be one indentation less.
Yes, apologies for that. Yes, I need to move this guy to this. Yes, thank you for the catch. Yeah, so I'm pretty sure you have heard about normalizing flows. There you go. It's just these two blocks of code, nothing else. You're done. You know how to code a normalizing flow in less than 100 lines. It's very simple. Of course, behind the scenes, there is a bunch of nice tools that Torch gave you, etc. So since I am preventing you to go for dinner, here's what I suggest. So tomorrow, I will try to discuss a bit how to train a normalizing flow. We are going to try to train it on some target density. So I will put some examples, and that's all about it. I put most of the material here. I will go over it. Feel free to read it, of course. If you are curious enough, try to go and implement the exercises so that you can be more fresh. But I promise you that at the end of the day, you will be able to construct a normalizing flow that it will mimic this density or any other thing at any other dimension, whatever you want. And we go from there, okay? All right, thank you guys. Good.
2 minutes. Any questions?
Okay. When are you holding a neural network boot camp?
I thought this was a neural network.
When are you holding a longer form one?
I don't know. So one thing that you can do is go to the slides and drop comments. I don't understand this, and I can improve it, for instance. That could be one possibility. I'm trying to make this thing as pedestrian as possible. I hope you don't get mine about that. But yeah, I don't have any other plans. I mean, maybe next year, it's up to Alexa, he's the boss. So
I will give up on applications of AI to nuclear physics. I'll continue. I guess, well, tomorrow it will be more access, which is more useful for applications. Right. Let's thank Nufu once again. See you at 6 o'clock. Very good. You don't like
yes.
Realmente pasó una